Our next talk is TPP, Transparent Page Placement for CXL-Enabled Memory. Hasan has defended his PhD at the University of Michigan under the supervision of Mosharaf Chowdhury. His interests are in addressing practicality challenges of memory disaggregation. He's going to join AMD as an advanced memory and CXL solutions architect next month. Thank you.
So hello everyone, I'm Hasan from Symbiotic Lab at the University of Michigan. Today I'm going to present our work on transparent page placement mechanism for CXL-enabled tiered memory system. So this work is done in collaboration with Meta, and it's currently being used in their production server for more than 1.5 years. So before I start, let's first discuss why CXL memory matters, what are its properties, and how today's Linux works on tiered memory systems. In today's server, we cannot design flexible memory subsystem because CPU and memory are tightly coupled together. They are usually connected through a specific DDR channels. So to increase the memory capacity, we need to increase the total number of memory channels, and we need to populate the DRAMs in power of 2 granularity. Besides, we cannot mix and match different types and technologies of memory with different bandwidth versus latency profiles. And when a new hardware appears, we need to upgrade the whole DRAM based on the CPU's requirement. Like with CPUs that support DDR5, we cannot run DDR4 together them. And this increases the total cost of operations in data center management. For example, in Meta, 40% of their rack budget comes from memory. And with every new hardware upgradations, they need to change all the memory together. And this eventually increases their data center expenditure every year over new hardware upgradations. CXL enables a finer grain server design by providing a flexible bus between CPU and memory. Through CXL interconnects, memories of different DDR generations can coexist together, and it enables different capacity to bandwidth ratio. We can also add cheaper and low power memory technologies in parallel to the DDR channels. And also, CXL enables the near memory computations by attaching accelerators to the CPU over the CXL interconnects. The prime benefit of CXL is it provides a byte addressable memory in the same physical address space. CXL memory appears to the OS as a separate NUMA node. All the memory allocations can happen through the standard memory allocations APIs, and CXL memory access is in terms of cache line granularity. All the consistency and coherency are maintained by the underlying hardware. In terms of bandwidth, it is also similar to the DDR channels. In some cases, the NUMA bandwidth can be even better than a dual socket systems based on how many links you are populating in your fabrics. And in terms of latency, it's also similar to NUMA access latency. It is expected to have hundreds or 150 extra nanoseconds over the NUMA access latency in a dual socket systems. However, these extra hundreds of nanoseconds of latency can often impact the data center applications if the memory is not optimally used. So to illustrate that, we run many data center applications in Meta server fleet. And for this reason, we come up with a setup where 20% of the working sets, workloads working set is supported by the CPU attached memory, and the rest 80% is supported by the CXL attached memory. So in this very constrained setup, default Linux cannot provide very good performance for cache applications because Linux does not automatically manage this page movement across different nodes. For this reason, we can see almost 14% drop in cache applications performance. There is another feature in Linux that is Autonoma, which can promote or demote pages from different tiers. But it also fails when the CPU attached memory is under very tight constraint. At this point, Autonoma's performance drops more than 10% for cache applications. And same happens for other applications like web applications or data intensive data warehouse applications. So this is obvious that to have better performance in CXL-enabled systems, we need to manage the memory systems more efficiently. And doing so in a transparent manner has some challenges. The main challenges is how we are going to handle the hot fraction of an applications. The more hot fraction of an application is supported by the more faster tier, that means the better performance. But this is not often doable because of the capacity constraint of CPU attached memory. For that reason, we need to figure out like what are the warmer or colder fractions of an applications, and we need to put them into a slower memory tier as much as can we do to make more room for the hot pages being allocated in the faster memory tier. But doing so in a very lightweight and less overhead mechanism is very hard because you may not always have a whole observability of your hot fractions. And there are also some cases where some applications have very specific needs. They have very specific sensitivity towards different page types. Some can be sensitive towards anons, where some others can be sensitive to the cache types of pages. So application-aware page allocation policy can often help many applications from the very beginning of their life cycle. And the next challenge is like which applications we should provide in this tiered memory system. Not everyone will have their benefit in such a system. So to understand that, we need to understand the characteristics of data center applications. We need to find out what fraction of their memory remains hot, warm, cold, how long a page survives in these systems, and what is the page access granularity. And to do so, we need a very specialized user space tool that can run without any kinds of application modification or any changes in the production environment. So for time constraint in this talk, I'm going to talk mostly about the first challenges, that is how we are going to efficiently manage hot fractions of pages. And to do so, we designed TPP, which is an in-kernel transparent page placement mechanism for tiered memory system. It employs a lightweight demotion mechanism for warm and colder pages. And this is complemented by an optimized and apt hot page detection and movement mechanism. TPP decouples existing Linux kernels page allocations and reclamation mechanisms to reduce latency overhead. And besides, it also introduced some optional page allocation policy, which is very specific to a certain types of applications. TPP is transparent to applications. You don't need to modify your applications. All of these TPP's components are within the OS level. And although it is designed mostly considering the CXL 1.0 or 1.1, it can be run with any tiered systems with like any multi-NUMA systems available in today. And this work, I said, is currently being used in Meta's production server for more than 1.5 years. A version of TPP's patch set has already been merged to the Linux kernel. You can find them from Linux kernel version 5.18. So before I discuss TPP's component, let's first see how page placement happens in today's Linux. In today's Linux, every node maintains 3 watermarks, min, low, high, to determine the load of those memory node. This watermarks indicates how much free memory is available in a specific node. So the default allocation policy is you allocate pages on the memory node attached to the CPU where the process is running. If the available free pages of that node goes below the high watermark, Linux kernel marks that node as a full and stop allocation pages to that node. It initiates the reclamation process, and the default reclamation process is swapping to disk, which is orders of magnitude slower, terribly slower actually. So when this reclamation is happening, new allocation goes to the next available node available in the systems, and later access to those pages have higher latency overhead. So however, when the reclaimer finds enough free pages to support the high watermark, new allocations can happen again on that node. So this is, it appears like both allocations and reclamation are somewhat dependent on same watermark thing. So as reclamation is a slower process, if your system has very high allocation rate, this allocation will halt every now and then because reclamation needs to catch up to find more free pages, and more hot pages will eventually end up in a slower memory tier, and that will increase the total latency overhead in the application lifecycle. And to in this regard, TPP initiates a faster demotion path. Instead of paging, TPP allows migration to remote node during the reclamations, and this is orders of magnitude faster than paging mechanism. To do so, TPP introduces a demotion list which tracks the inactive and warmer pages of a node. So during reclamations, TPP initially scans the inactive files and then inactive anon pages, and if that's not enough, then it moves to active file and then active anon pages. And after finding the demotion candidates, it initially tries to migrate them to a slower memory tier. And if that migration fails for some reason, like the CXL node is not available or it fails because the node is full, then it falls back to the swapping mechanism. And this is for the traditional backward compatibility. TPP also allows faster memory allocations through optimized data path. It decouples the allocations and reclamations logic we mentioned earlier. And for doing so, we introduced two separate watermarks responsible for both work. One is for the allocations and another one is the reclamations. And in TPP, when these reclamation watermarks can be configured to trigger early, by default, we trigger this reclamation watermark when X% of the capacity is full. So if the X% of capacity of the memory node's capacity is available, then we can actually initiate the reclamations and it can trigger much earlier. Allocations to the local node can happen as long as free memory does not cross the allocation watermark. So this watermark is kept lower than the reclamations one, so that allocations can happen even if a smaller amount of free memory is available. And this extra headroom always allows reclamations to catch up any burst in the allocation request, which eventually helps more pages to end up in the faster local node. And we provide a user space interface to configure the reclamations watermark in runtime. In terms of promotion, we utilize the concept of autonoma, but we make it much optimized. We periodically sample a subset of pages in CXL address spaces and poison their page flags. Here, we don't sample the faster memory tier node because the memory residing in the faster tier, they have nowhere to go to be promoted. Moreover, our allocation policy is in such way that most of the hot traffic can be supported from the faster memory tier. So the overhead of scanning and page fault reduces significantly by simply scanning the cold pages staying in the CXL memory node. So whenever a CPU tries to access the sample pages, it causes a minor page fault. And after having a NUMA fault, we consider the page activeness to promote it back. If a page is in the active LRU, it has very high chance to be hot again. And in that case, we immediately migrate the page. If it's not in the active LRU, we put it there and wait for another NUMA hint. And that NUMA hint, if comes within a very short time, then we find, okay, this is very high chance of being hot later on, and then we migrate it back. And TPP appears in today's Linux as a autonoma mode. One can use NUMA balancing normal mode to enjoy today's vanilla autonoma mechanism. This is for backward support. And NUMA balancing memory tiering mode is for enabling TPP in memory subsystem. In terms of evaluation, we run 4 different types of application across 3 main service domains in Meta server fleet. We use 2 prominent caching applications, 1 social media, and 1 data warehousing applications. In our evaluation, we find that TPP's optimized allocations and data movement policy can handle burst even more effectively. Because of this watermark decoupling, TPP allocates 1.6 times more pages to the faster tier memory node. And always having a free headroom in the fast memory tier can allow more promotions to happen, more promotion of trapped hot pages. So promotion in TPP is 30 times faster than its counterparts. In terms of overall performance, based on applications access pattern, TPP can improve the throughput by 17% for these 4 applications. So in summary, TPP is a transparent page placement mechanism for tiered memory systems. With its lightweight demotion and better promotion and the optional workload aware allocation policy, TPP helps improve the performance of data center applications in a tiered memory systems. And that's all from me. I will be happy to have any questions from you.